is Joe Cohen, and I'm the president of Filtrasonics. We're located here in the Mile High city of Denver, Colorado, and I'm out here today in all this thin air in our R&D shop, which you know stands for Research and Development. What we want to show you today on this video is high flow water filtration and a new technique that we've developed. We're first going to show you the three conventional types of high flow water filtration and the associated inefficiencies and malfunctions with them. Then we're going to show you a new technique that we've developed and patented right here in Denver called radial flow filtration, short version RFF. So for the first step, I'd like to go over to the table here and just show you the three types of conventional high flow water filtration, and we're also going to cover the untalked about inefficiencies and malfunctions that coexist with them. So first, let's step over to the table here and let me give you a quick show. Okay, so let's make sure that we understand what we're talking about. We're talking about water filtration, and you have to remember first that water is a universal solvent of the world. Everything's dissolved by water. And the techniques used to remove dissolved impurities is not filtration. That's different techniques. Filtration is removing suspended solids, things that are suspended in the water in the way of dust and grit that you can see if you magnify the water. Basically taking the water from a mud quality to a clear quality. And it's the main universal thing that has to be done in every water cleaning process around the world. So I mentioned we have three conventional methods of doing this. The first one is called cartridge filtration. Pretty simple, really. You have a pleated filter that the water runs through, gets cleaned and taken back out. And because of all the pleats, you have a lot of area and a lot of appetite to catch a lot of stuff. But once this thing's loaded, it has to be manually changed or manually cleaned. So you have a good filtration technique that never violates the filtered water, has a huge appetite, does a great job, except if you're handling a lot of bad water, this technique is going to take a lot of labor to clean and replace cartridges. That's the drawback to cartridge filtration. The second type of conventional high flow water filtration is called diatomaceous earth. Diatomaceous earth, or you can call it DE, is simply ancient marine plant life that's been mined. It forms a white powder. It's a sacrificial medium. It goes into a backwash filter. It does its job on the water, a wonderful job. It filters down to 3 microns. That's why it's commonly used in water treatment plants. Beverage manufacturers, breweries use it. It's commonly used on swimming pools and aquaculture. However, when you backwash this backwash filter, you sacrifice the media and have to add more. So the diatomaceous earth is first put into a slurry that's fed into the filter. Basically you mix this with the water and shake it up and you've got a slurry. Looks like a milkshake. And what that slurry does is it's pumped into the filter that has a series of cloth grids. So that slurry comes in to grids that look like this, and they have a fabric, and it forms what's called the cake. And it's about 1/8 inch thick. It does a wonderful job. It has an extremely slow flow rate. The water flow rate through a diatomaceous earth filter is at the speed of 3 inches per minute. So when you go to backwash the cake back off, that's the speed, 3 inches per minute. That doesn't really move anything. You can't wash your car or your body with water going that slow. So there's a lot of problems with diatomaceous earth. The filtration process generally calls that you go to a backwash cycle for a minute, back to filter for 30 seconds, back and forth 5 times. The grids have to be pulled from the filter once or twice a year, cleaned with acid. They tend to bridge together. Quite a few problems. In commercial industrial applications, when the cake is on there doing its job, it can crack. So if you have a pressure surge or a flow change, the rigid cake can actually crack. Another problem is your grids will bridge together. From repetitive backwashing, you don't get all the DE out. So the first thing you know, it starts growing and growing and growing, connects to the next grid, you lose surface area. In conclusion, you have a really good filtration process as far as how well it cleans the water, but it's very, very labor intense. It has to be cleaned too often, it doesn't backwash well, and the media is sacrificial, so you continually have to add more diatomaceous earth. Okay, let's go into the third conventional method of high flow water filtration, which happens to be the oldest and the most popular. It's called the sand filter. Imagine this is a filter tank, and you fill the tank with sand. There's a plumbing assembly called an under drain and a distributor at the top, and it downflows the water through the sand. And the sand cleans the suspended solids, the mud, to clean water. The way it works is the water goes through the passages between the grains of sand, which are called interstices, and they trap the suspended solids. Now, as those get plugged up with the suspended solids you're removing from the water, they resist the flow and stop the flow of the filter. To clean it, simplest filter in the world. You reverse the flow, it's called backwashing, and the bed fluidizes, and it's kind of like washing your hands, rubbing your hands, the sand is all moving around, turns loose of the contaminants, and then it's put back to normal flow and it's ready for the next filter cycle. Permanent media, backwash filter, easiest to operate. Let me show you three of the problems. First problem, if your filter tank is out of level, which happens pretty often, the sand stays level from the water flow, but you end up with a short route through here and a long route through here. So all the water tries to go through the easiest way, the short route, and it causes filter malfunctions that also reduce the appetite of the filter. Next problem, and a common problem, is called high flow channeling. If you run the water flow too fast through the sand filter, it temporarily digs a little vortex, a little tornado in the sand, like I'm doing with my finger here. And so then you let the water pass through from the top to the bottom of the sand bed without being filtered. So you have a malfunction. And the third problem I was going to tell you about is called low flow channeling. If your tank is level and the sand's level and everything's fine except one little thing, you're running at a super slow flow rate. Water will take the easiest path of least resistance, and it'll go down the side of the tank, which is like a water slide between the sand and the side of the tank, go to the bottom, low appetite, malfunction, that's called low flow channeling. So next on the sand filter, I'd like to show you the process in action. So we're going to step over to a piece of equipment over here where I can actually show you the sand process and what it looks like. Okay, now let's have a little bit of fun. This is Filtrasonics' answer to Robot Wars. This is our granular media tester that we lovingly call R2D2. I've got silica sand in it today, 14 inches, just like the regular bed of a sand filter, and we're downflowing at the same velocity, the same flux rate as a sand filter, which is 20 gallons per minute per square foot. Slow, ½ inch per second flow rate. What I'm able to do with this piece of equipment is reverse the flow. Like in the backwash cycle, we're going to simulate a backwash, and you can see the media body expand and fluidize like washing your hands. So I turn the two valves. Now I've got it in reverse flow at the standard flux rate. You can see the backwash cycle is expanding the media body, and all the grains of sand are now washing themselves, which is impressive until you consider the water flow rate here is only ½ inch per second. So it has to clean all the sand, and when it finally gets done, you have to handle the freeboard of the filter. So that's all the water above this expanded body has now got to be displaced before you can go back to the filter cycle. Very wasteful. How wasteful? I'll tell you how wasteful. This is 1 pound of ISO test dust, what we use to test filters. This to be removed in this process takes 195 gallons of water. Now, I can walk into the men's room, you stay here, and pour this in a toilet and get rid of it with 3 gallons. A lot of inefficiency that result in bad water conservation that can be improved. So next, I'm going to put it back into the filter cycle, and I'm going to show you another problem. I turn the valves back to normal flow, and the sand resettles into the filtration mode, and you'll notice a white line here at the top. That's how the fine particles settled at the top. By the normal laws of physics and stratification, all the fines are at the top. But in filtration, by logic, you want to start coarse and work fine. That's how you catch a lot of stuff in water. In the sand filter, it tends to work backwards. So we have outlined all the inefficiencies of the sand filter, all the flow-related problems. Next, let's step over here, show you the solution.